Well, thank you all very much for showing up this morning. I think we're in for a very exciting talk, and it's my pleasure this morning and privilege to introduce a colleague of mine, Dr. Kristin Lennox. She's presently the director of the Statistical Consulting Service here at Livermore. You've been here for 5 years next month. She came to us after completing her graduate work at Texas A&M. And I think at the time that you've been here, you've touched almost every part of the laboratory. And notably, about 2.5 years ago, she reestablished a statistical consulting service here, which is something that the laboratory hadn't had in about 30 years. And I think over the course of the last 2.5 years, there have been about 50 different projects with researchers from around the laboratory that you've been engaged in. She's managed a team of, say, 8 to 10 statisticians and data scientists that have been involved in these engagements. And so I think the talk that you'll hear today pulls on a lot of the things that she's observed in the course of that process. And so let me go ahead and turn it over. Kristin?
Thank you so much, Paul, for that introduction, and thank you all for coming out here today. I have a confession to make. I'm not actually going to cover everything wrong with statistics this morning. It's a 90-minute talk. We could only get the room for an hour. So what I'm going to talk about today is, as Paul said, based on my experience doing statistical consulting, it's what I like to call statistics in the wild. It's basically what happens to statistics when there are no statisticians in the room. If you've ever practiced statistics, you know there's typically not a statistician in the room. And you might well ask me, how do I know what's going on when I'm not there? Well, I've been doing statistical consulting off and on for about 10 years now, and something that happens a lot to statistical consultants is some subject matter expert, a scientist or an engineer or what have you, will go out and they will collect some data, sometimes via experiment, sometimes not. They will then do statistics to it. They will then bring it to me, and they will ask me what I think of what they did. This is a suboptimal way of utilizing a statistical consultant because quite often I think they ought to have talked to me sooner. However, since coming to the laboratory in particular, there have been a regular stream of people who show me the statistics that they did, and I say, great job, that's what I would have done. In some cases, that's better than what I would have done. So the question I've been thinking about for the last few years, and the point that I'm going to try to make in this talk, is that there are certain habits of mind, if you will, that allow people who perhaps don't have 2 to 5 years of postgraduate studies in statistics to nonetheless be extremely successful in applying statistical analysis to their own work. So this isn't a talk that's trying to scare people off of statistics. I'm trying to make every single person in this room and beyond the best statistician they can be, and I believe that that's actually going to be quite good. I will get to how that's going to happen in slide 7, but in the meantime, in the abstract, I did promise you a crisis, and we do in fact have one. So I believe this is sort of a two-part problem. Part of the issue is a PR situation we're suffering from right now, where there's this hot new field called data science. It encompasses statistics, predictive analytics, machine learning, a lot of these sort of buzzword professions right now. And data scientists don't tend to speak highly of statisticians. We're viewed as the troglodytes of the field. We're obsessed with limit theorems for some reason. We only use boring methods like linear discriminant analysis and linear regression, lots of linear stuff, which is old. And we don't use the cool new methods like random forests or kernel density estimation, which were both invented by statisticians, by the way. So the situation isn't that statistics is being left behind and that we don't have exciting new methods that are being used for exciting new problems. It's that when people hear statistics, they only think of the boring old stuff. So that's something of a personal problem that comes up among statisticians when we're invited to dinner parties. There's actually a much more serious problem going on in science at large, which was very well summarized in this 2005 paper by John Ioannidis. He's an MD, PhD, and he was trying to address the problem of non-reproducible results, in particular in biomedical science, which is his field, but it's a lot broader than that, where we are seeing a large number of papers. His argument is a majority of papers, even ones that are published in highly reputable journals by highly reputable groups, that when someone comes back and tries to replicate their results, they can't do it because the results were spurious. They were false positives. And this paper was very well received in the technical community at the time. It got a lot more press in 2010 when an article in The Atlantic came out called Lies, Damned Lies in Medical Science. As you might be able to guess from that title, a lot of the blame for this problem is laid upon statistics. So at a very high level, there's a method called null hypothesis testing, and its harbinger, the p-value, which you might have heard of before. And the way that p-values work is that if you have a p-value greater than 0.05, your paper can't be published. If you have a p-value less than 0.05, congratulations, you get tenure. And so we're in a situation where true negative results, these high p-values, are never published. And because there is actually a known false positive rate when you're using these methods, a lot of the positive results that are being published turn out not to be real. And this is a very serious problem, and it's prompted responses both serious and somewhat less serious. So there's actually a journal called Basic and Applied Social Psychology that has banned statistics. Technically, it's only banned frequentist statistics, but it went a lot farther than saying, okay, you can't use p-values in null hypothesis testing. They said, you're not supposed to use power calculations, you're not supposed to use confidence intervals, you're not supposed to use any of these tools, which have not, by the way, been implicated in the larger problem, but it's still okay to use Bayesian stuff because we haven't read anything bad about it in the Atlantic so far. The mailing list that I subscribed to where I first heard about this event summed it up very nicely by saying that they've admitted that they've been using a crutch and now they've put on a blindfold. There have also been more constructive, but still what I view as suboptimal responses to this problem. The journals Science and Nature have both implemented a statistical review process, where when a paper comes in, if it has a substantial statistical analytical component, they've partnered with the American Statistical Association to ensure that there will be a professional statistician on the review team for that paper. So this is a good way of making sure that really egregious statistics doesn't make its way into very fine journals, but it's not the real solution to this problem. As I mentioned in my preamble, when you come to a statistician after you've done the experiment, I think that Ron Fisher put it best when he said, it's a little bit like performing an autopsy. We can perhaps tell you what the experiment died of. So this is going to lead to, hopefully, a reduction in poorly practiced statistics, but it's also going to lead to an increase in scientists who really don't like statisticians very much. So you can imagine this is a serious problem, and statisticians and scientists in general need to look at how we can address this. And I think it's very important to start with, how did we get to this point? Well, the beginning of the story is actually very happy. The statisticians won. Over the course of the 20th century, people became convinced that the right way to learn about the natural world, the right way to make engineering decisions or business decisions or all kinds of decisions is to use data. And the right way to use data is to use statistics. So all of a sudden, we've created this enormous demand for statisticians and other people who are trained in these methods to basically analyze all the data that's coming in. And if you look at what's been going on in the last decade or two, you know that the amount of data available for people is just increasing at an exponential rate. So everyone's looking for statisticians, and no one can find them anywhere. So there are a variety of reasons for why this happened. One of them is there's a comparatively high bar to becoming a statistician. Up until recently, undergraduate degrees in statistics were very uncommon. It was thought that you should first get your undergraduate degree in something else, preferably mathematics, and only then could you be introduced to the higher mysteries for your master's degree and later your PhD. So we're already setting a high bar because you have to be a mathematician to start before you can do this, and we didn't have that many mathematicians when we started. Secondly, we have an issue with incentives, particularly in the academic statistics community, where the way that you acquire glory and a highly regarded statistical name is by developing amazing new statistics and publishing in the Journal of the American Statistical Association and Annals of Applied Probability. This is one of the few fields where a Nature paper isn't going to impress anybody because that just means your collaborators are good. You don't get a whole lot of points for doing really good statistics on really important problems if those statistics were invented in the 1950s. And unfortunately, they invented a lot of good things in the 1950s. So if you happen to have a serious statistical question, but you don't happen to have the latest, greatest, newest data that's going to get somebody a JASA paper, you go looking for a statistician, and that's going to be a very frustrating exercise. It's not quite that bad, but it's, again, not a productive enterprise in many cases. So the non-statisticians are intensely frustrated. They can't find anybody to help them. The statisticians are intensely frustrated because they just want to go back to their whiteboards, but people keep pounding on their doors asking for them to do boring stuff that Fisher invented. The solution that people came up with is, okay, we're going to train non-statisticians to do just enough statistics to solve their problems to get them to leave us alone. And unfortunately, that statistics training, which is remarkably standard actually across the country, is not working. So I'm going to refer to the standard first and frequently only statistics course that people take as Stat 101. Please raise your hand if you took Stat 101. It would have involved a test of a single proportion, maybe two proportions, p-values, confidence intervals, that kind of thing. Okay? All right, that's a majority of people in the room. How many of you made it all the way to Stat 102, which would have involved experimental design? You might have heard the word randomized block. I see one person in the back. My group leader is now raising his hand, but still, many fewer people. How many people made it farther than that? Okay, not very many at all. So the point is, most people receive this standardized introductory training and then nothing else. And I think that the problems that we're having in statistics, both the PR problems, where people fundamentally misunderstand what we do, and also the larger scientific cultural problems, where statistics seems to be getting a lot of journals and a lot of researchers in trouble, are caused by the way we teach that one class. So I used to teach Stat 101. I am part of the problem, so I'm now trying to become part of the solution. Stat 101 can be taught in a variety of ways, some of which are quite good. If you actually read the textbooks or you have a really good professor, they will touch on how statistics really works. But if you're an undergraduate and you want to pass a class, you may or may not pay attention to that. The way you pass tests in Statistics 101, certainly the way my students were passing tests, was very procedural. You could basically make yourself a decision tree or a checklist. You'd be reading through the test problem, and you would check your data type. And let's say, okay, I have two numeric variables. I only know one thing you can do with two numeric variables. This is a linear regression problem. Then the second thing you do, you read through, you try to figure out the inference method you're asking for. There are a few more steps. Hopefully somewhere in that ... there's some assumptions checking. And then the final step is you play statistical Mad Libs. And you say something like, because the p-value is 0.06, we fail to reject the null hypothesis at the 0.05 level, and we do not conclude that blah, 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 blah. It's really boring grading these tests, by the way, as well as taking them, I'm sure. So the problem with this approach to statistics, which we reinforce by grading you based on your ability to do this, is that real statistics doesn't work that way at all. Thankfully, my job is not to retreat to my office and look up an answer in the Handbooks of Statistics volumes 1 through 57 and work my way through this agonizingly long checklist. My job is so much more interesting than that, because what statistics really is mathematical modeling under uncertainty. So on the one hand, it's a lot simpler than having to deal with the Handbooks of Statistics volumes 1 through 57. On the other hand, you can't ever turn your brain off when you're doing statistics. You have to be thinking about your problem all the time. But as long as you know how to approach the problem and how to think about the problem, you can avoid these pitfalls that we're seeing throughout the scientific literature and the statistical literature today. I'd like to raise another point about Stat 101. We have all these high-profile articles about problems with statistical applications in science and the banning of p-values and all of this stuff. Absolutely nothing stated in any of them is news to statisticians. The problems with p-values have been known pretty much since they were invented. They've regularly appeared in the statistical literature since then. Somehow we are failing to communicate that to the vast majority of scientists who are trying to use them in their day-to-day research. So how do we fix this? Well, I have made a plan. It has 3 steps because plans with more than 3 steps are never fully executed. So this talk is intended to address steps 1 and 2, where I want to show you why you shouldn't be doing cookbook statistics. Using real examples from the lab and the wider world, why does this sort of automated checklist cooking approach not work? Where does it break down? Second, I want to show you a better way to approach these problems, which I'm calling statistical thinking. This is what statisticians really do. And finally, in situations where you don't feel that you can quite handle it on your own, or you want a wider view of the literature in statistics, or you're just not quite sure how something works, we do have statistical help available. And I will definitely give you contact information for that at the end, as well as some ideas of the kinds of things we can help you to do. So back to number 2. What is statistical thinking? I think that you can understand it best by going through the golden rules of statistics, the first of which is know thy problem. I don't think I mentioned before, this is an applied statistics talk, so I'm not going to help you improve your limit theorems. I assume that you have some problem in the real world that you're trying to solve. You're trying to understand some kind of natural phenomenon. You're trying to make a decision. You're trying to assess risk. But there's always some goal in the real physical world that you are trying to achieve. You have to keep that goal in mind at all times, preferably the front of your mind, at worst at the back of your mind, but never take your eye off the ball, so to speak. Second of all, know thy tools. This goes a lot farther than the Stats 101 checklist approach, where you figure out which of the methods you're going to use and then you check a bunch of assumptions. I have really bad news for you about statistical assumptions. They are very nearly always violated. So it's not enough to know how your tools work. You have to know how they break. You have to figure out when you can still use them, when the assumptions that underlay them are violated. And fortunately, we're the kinds of people here who use models in other contexts, so we know that assumptions are always violated, and you can figure out how you can use the models anyway. Finally, know thy data. So this is out there for all of my friends in data science who have argued that the problem with statistical methods is that they're all parametric. Parametric models, of course, are reliant on parametric assumptions, but if you can just get enough data, you can let the data speak for itself, and the data won't lie to you, unless you have the wrong data, which is actually a problem that comes up a lot more than people think it will, and I'll walk through a number of high-profile examples where that's been the case. But back to number 1, know thy problem. So I want you to think back long ago to your undergraduate days when you were taking Stat 101. How did you determine what the right kind of analysis was to do when you were taking an exam or doing the homework? Easy. You look at the data. As I said before, you have 2 numeric variables. You only have time to learn one thing to do with them. You're going to be doing linear regression. That's not quite how it works in practice. In the real world, the right data to collect and the right methods to use depend on the goal that you're trying to accomplish. You have to watch out for data myopia. Just because you have some data doesn't necessarily mean it will help you. And I'd like to sort of highlight this point with an example that I call the $1 million binomial distribution. This was one of my very first consulting projects at the laboratory, and it related to the National Ignition Facility. So for those of you who are visiting the laboratory and maybe aren't familiar with NIF, it is the world's largest and most energetic laser array. I could talk about it for an extended period of time, but for the purposes of this example, you only need to know 2 things about NIF. The first is that the kind of science that we do there cannot be performed anyplace else on Earth. It allows us to answer questions that can't be answered any other way. The second thing you need to know is that it was very, very expensive. We want to take good care of it because it costs a lot of money to build and it costs a lot of money to run. But that has to be balanced with the fact that, again, we need answers to questions that we can't get any other way. So any problem that NIF has that impacts its ability to do science is, by definition, an expensive problem. And a couple of years ago, NIF developed a very expensive statistics problem. So it was during a regular maintenance period, NIF was shut down, and they were installing a particular component, which was a fail-safe device. One of the engineers involved in the installation determined that the fail-safe itself could fail in a very unsafe way. It was described as a catastrophic damage scenario, which doesn't actually mean you're going to have like flames leaping out of the laser bays or the building falling down or anything, but it could create extremely severe damage to 1/3 of the optics at NIF, which means I see Wint saying, yes, that is a very, very serious problem. You've probably figured out I'm understating the cost impact in my title. So it's very serious. We want to avoid having that happen, but again, we don't have the option of not running NIF just to keep it safe. There's always some aspect of risk when you're doing big science, when you're doing something no one's ever done before. And NIF actually has protocols that they can follow that allows them to weigh the risk to the system against the value of the science. And they were able to perform a calculation against their standard protocol and determine, all right, what's the maximum risk that we can tolerate for the failure of this component? And they determined that they could continue to run the system if they could prove that the failure rate was less than 1 in 10 billion. As I said, it's a very expensive system. We want to keep it very safe. So they went to their engineering reliability textbook. They did exactly what they were trained to do. They looked up the right formula. They put it in a spreadsheet. They said, okay, 1 in 10 billion, and we need to certify this many components. How many tests do we have to run to achieve that certification? Now, I can tell you if this were anything other than electronic component, this testing would not be possible. You want to certify something at a rate of 1 in 10 billion, you're going to be doing more than 10 billion tests. However, the testing rate for this component could be measured in hertz, so it was technically possible. It was just going to require NIF to be shut down for 3 months. This was not popular. Of course, they had plan B, which is we can just operate NIF outside of the agreed upon risk bounds for 3 months. This was also not popular. So they're facing two options that they don't like very much. And then someone has the brilliant idea, none of us do statistics for a living. Maybe we can find someone who does, who'll come in and look at this and hopefully tell us we've done something wrong. So this led to a chain of phone calls, which culminated in my boss's boss's boss pulling me out of a classified meeting and informing me that NIF had a statistical emergency, and I had to be there in an hour. Up until this moment, I hadn't believed there was such a thing as a statistical emergency. It always seemed like something that could wait. I learned otherwise. So I'm at this meeting, I'm sitting next to the person who performed this sample size calculation where they'd come up with a 3-month time frame, and they say, okay, well, this is how we came up with the 1 in 10 billion bound, and that looked pretty good. And this is the formula we were using to calculate the sample size, and unfortunately, that also looked correct to me. So the popularity of statistics at NIF is really tanking at this point. Very fortunately, the engineer sitting across the table then speaks up and says, I think we should be taking credit for the other component. My ears perk up. And I said, what other component? Turns out this fail-safe device is in series with another component at NIF, and in order for disaster to occur, they both have to fail simultaneously and independently. And it turns out that bounding 2 things at less than 10 to the minus 5 is a lot easier than bounding 1 thing at less than 10 to the minus 10. 5 orders of magnitude, it matters. And so we were able to repeat the calculation for both components simultaneously, and it turned out they'd already done that testing in the course of regular maintenance. I think one of them took a few hours, the other one was slower, it took a few days. But again, absolutely no need to shut down NIF, absolutely no need to operate outside the risk parameters. The statistician is a hero. And you better believe that's what I wrote on my performance appraisal for that year. Although it wasn't actually true. The hero in the room was the engineer across the table, because I would never have known that this was a 2-component problem. And what that person did that no one else in the room was doing, certainly not me, was recognizing we don't actually have to worry about this one fail-safe component. We have to worry about all of NIF. So when you were able to take a step back, when you were able to escape that data myopia, we were actually able to solve the problem in a much better, much less expensive, and equally credible way. And so that's what I mean when I say know thy problem. Don't lose focus just because you have certain data and you know certain methods. If they're not addressing your problem, then you need to look a little bit deeper and a little bit farther afield to figure out what you're going to do. All right, commandment number 2, know thy tools. Way back in the day in Stat 101, you were told that we pick our methods according to the data we've got and according to the correctness of the underlying assumptions, and you already know what I'm going to tell you about that. The second thing you learn in Stat 101 is that statistical procedures, as long as you follow all the rules, are going to yield unambiguous results. It's a lot like baking. You do the same thing every time, you get a desirable result. I wish this were true. Unfortunately, statistical models work the exact same way every other model in science or engineering works. Its validity depends on the context, and the results can be open to interpretation. So I underlined the word models there because I'm going to make the argument that statistical methods are all models. Sometimes this is fairly intuitive. So the equation that I have up there is the linear regression model. You have your response. It's a linear function of your explanatory variable x, and then you have some error model epsilon. The plot up there is showing independent identically distributed normal errors, the classic Stat 101 error model. And people look at that and that looks like a model to them. What about that? So that is x bar. It is the shorthand notation for the arithmetic mean. The arithmetic mean is what I like to call a reflexive statistic. If you've got some data, why not take the average? People do this all the time, often in Excel. But what do they mean by taking the average? What is that number representing to them? Well, usually, when people are taking the average, they say, this is a typical member of my population. This is a representative example. I would expect some of the data to look like this, actually a good amount of the data to look like this. And that's true as long as your data looks kind of normal, or at least unimodal and symmetric. So when you're using the mean as a representative member of the population, you are actually using a statistical model. You're making assumptions about the real world that will not hold if, for example, your data really looks like that. So when people calculate the mean of that distribution, it still works for some things, like if you had a bar and that's the weight distribution, you're still going to find the balance point. But if you say, I want a typical member of this population, you're actually going to get something that's in that trough there, which is not usually what people want. So if I, for example, wanted to talk about a typical example from this population, I'd probably use two numbers. I look at the peaks of the two clusters that you have there. So keep in mind, anytime you do statistics, even very simple statistics, in order for it to be useful to you, in order for it to solve your problem, you are probably making some kind of assumption about how the world works. So I've told you, statisticians view our methods as models, even the very simple ones. Now I'm going to tell you how statisticians view their own models. So George Box, very, very famous statistician, perhaps most famous outside of statistics for this quote, which is, essentially all models are wrong, but some models are useful. So we never actually believe the assumptions that we put into these models, that we put behind these models. They don't have to hold exactly. They just have to hold well enough for us to be able to address whatever our concern is. And that's a lot less comforting than the Stat 101 approach, where all you have to do is look at a bunch of plots and maybe run a test, and if everything comes out fine, you're home free. But that's not how it works in real life. So I'm going to give you an example of how seriously statisticians really take their own models. So this is an explosive safety example. The device that you see in the photograph is called a drop hammer. It's located at the High Explosives Application Facility on site. It's used to test the impact sensitivity of explosives. So what you do, you take a very tiny sample of explosive, you crank up the drop hammer to a particular height, place the sample underneath it, drop the hammer, and then you check for a very tiny explosion. We know they're very tiny because we've been using the same drop hammer for years. So they actually check it. They look for a flash or they look for some kind of acoustic signature, but it's not a particularly dramatic effect. So what's interesting about the drop hammer is it lends itself to one of my favorite areas of statistics, which is adaptive experimental design or sequential experimental design, which is to say you can't test more than one sample at a time. You have to do it one at a time, so why not use everything you've learned so far in your test series to pick the next point you're going to look at? And one of the earliest examples of a drop hammer experimental design specifically was this paper by Dixon and Mood, which was published in the Journal of the American Statistical Association in 1948. So this paper has impeccable statistical pedigree. The way the method works is that you assume that your data has a normal distribution. So what's our data here? Well, you say every single sample of explosive that you can take has some critical height, where if you hit it above that height, it's going to pop. If you're below that height, you're not going to get any kind of reaction. Actually, they don't assume that the heights themselves are normally distributed. They assume it's a transformed height, specifically the log transformation in this case. So you never actually observe the height in question, but we're assuming that it's normal. You also assume that you have some reasonable guess of what the mean of that distribution is going to be. It doesn't have to be exactly right. Some reasonable starting guess of what the standard deviation of that distribution is going to be. Again, doesn't have to be exactly right. And then the way you proceed with testing is you start with your mean, and I'm going to kind of follow that example plot I have up there. So you start with the drop hammer at your mean height, you drop it. In this case, we saw a reaction. So we're going to move the hammer one standard deviation lower. So we're going to put a little bit less energy into the system and see what happens. We drop it again. In this case, it pops again. So we're again going to move it one step lower. We drop it again, nothing happened. Okay, raise it a step. And up and down and up and down and up and down for usually 50 to 60 tests. This method is often called the Brewston up and down tests for reasons that I think are fairly obvious based on this description. So I mentioned that there's a normality assumption underlying this. And there's something critical to think about with that normality assumption, which is you can never check it. You don't have a whole lot of data to start with, maybe 50, 60 replicates. And none of that data directly samples the distribution. All you have are a bunch of zeros and ones. And for that matter, you never actually move away that far from the center of the distribution. You're typically staying within 2 standard deviations either way. You can't check normality for this data. So what do Dixon and Mood have to say about that? Well, what they say is that that's okay. Your transform data doesn't have to be normal. It has to be reasonably normal in the neighborhood of the mean. They intend for this method to give you information about the mean of this distribution, and it'll work as long as your data is, say, symmetric, roughly, unimodal, and the tails aren't too horrible. You don't have to prove the normality assumption because you don't really need it. So again, this model is wrong, but it's very useful for this application, as evinced by the fact that this was published in the premier statistical journal in the United States, and a statistician is standing in front of you today and saying, I have no problem with this. So now I'm going to show you statistics gone wrong. And it looks a whole lot like statistics gone right, doesn't it? We have the exact same data, we have the exact same method, but something has gone awry. I'll give you a hint. In Dixon and Mood's paper, they have the following quote: "The up and down method is particularly effective for estimating the mean." As I discussed before, it's fairly robust. "It is not a good method for estimating small or large percentage points, for example, the height at which 99% of specimens explode, unless normality of the distribution is assured." I added the emphasis there, but in the very next sentence, they basically say, you're never going to assure normality, so just seriously don't do it. Statisticians believe in the normality assumption the same way we believe in asymptotics. You don't have a normal distribution any more than you have an infinite sample size. So you cannot rely on the assumption when it matters. So to give you an idea of what people do with this, Dixon and Mood said, don't go out to 1%. Don't go out to 10 to the minus 1. That's in a normal distribution, which again we haven't got. Between 2 and 3 standard deviations away from the mean, they stop trusting their method. People go out routinely 5 and 6 standard deviations from the mean. This is extrapolation in a very bad way. So if you look at the data that you're collecting, that data is all within about 2 standard deviations. If we go out about 6, your data's in the figure, your inference is in the text box. Your data has nothing to say about what's going on down there except it's below the median of the distribution. And you absolutely should not trust it. But people do this all of the time. So I not only work with the explosives testings folks here, I also do peer review for other laboratories. And I had a very interesting experience reviewing a paper for another laboratory, which is going to remain nameless, but it's located in New Mexico. You still don't know who they are. And I was reading through a paper, and it was a testing situation, wasn't the Brewston up and down test, but a similar situation where they had a very limited sample size, and then they were going out 5 standard deviations from the mean, and assuming normality, and quoting those numbers like they were real. So I knew these people, and I knew they were smart people, so I gave them a phone call. And I said, you cannot possibly believe this. They said, of course we don't. But we have to put it in the paper because everybody else does, and people are expecting to see it. I did not view this as a credible defense. So the compromise solution that we came up with at the end of the day was the paper went out, the 5 sigma numbers were still in it, along with a disclaimer saying, by the way, we don't actually believe these numbers because obviously the data isn't normally distributed, but we're putting this here because it's standard in the literature. Not perfect, but it was better. But the point is, when you're dealing with a method, you have to make sure that it's robust in the regime where you're using it. If you really want to talk about tail distributions, there are different testing methods that you can use that are better for that. When you're talking about extreme tails, unless you're NIF, you're never going to be able to get enough data. But you have to be very honest about the assumptions that you're making, why you believe them, and whether or not you really need to believe them when you're quoting those kinds of results. All right, so you can't have a talk about everything wrong with statistics without talking about null hypothesis testing and p-values. Please note the disclaimer. I speak only for myself today. I do not speak for Lawrence Livermore National Laboratory, certainly not the Applied Statistics Group, my group leader, especially not my advisor, who is in fact a Bayesian. I don't think there's anything wrong with p-values. I use them in my statistical practice. But however you are using them, you need to recognize that a p-value of 0.0501 is the same as a p-value of 0.0499. One of these is not a cause for despair, the other a cause for joy. So be careful of that. I don't have a problem with statistical hypothesis testing. I use it in my statistical practice. It is not the correct tool for making all possible decisions. Complaining that null hypothesis testing doesn't work for making all decisions in inference for all of science is a little bit like saying that your screwdriver is broken because it doesn't work on nails or put out fires. That's not what it's supposed to do. It works in a very limited context, and neither of these are really automatic methods. You always have to be thinking about the implications of using them, but overall, they're not broken. They're just misused. That said, do not go back to your office and say that the director of statistical consulting said it's okay for you to use p-values in null hypothesis testing. That's not what I'm saying. I'm saying that they are valuable in a particular context. Be willing to invest the time to understand them if you want to use them. All right, last topic of the hour, know thy data. So this statement is what you hear a lot from people in data science, predictive analytics, machine learning outside of the statistical community, basically the kind of big data community. Of course, parametric models are vulnerable to violations of the assumptions. But if you can get enough data, and in some contexts you can, then you can use robust models that aren't sensitive to these assumptions, and all of a sudden the kind of cookbook approaches, these very standard sort of software approaches, Google's robot statistician, that kind of thing, they're all going to work in a way that they didn't in the small data statistical context. I don't buy it. So there are a lot of reasons why I don't believe this. There are actually a lot of caveats and sensitivities to the kinds of models that are used for big data that really do affect its performance in real-world problems. But the number one issue with big data approaches is the same as a huge issue with small data approaches. You have to start with the right data. And this is harder than people believe. So there's a very famous probability problem called the Monty Hall problem. Lots of people encounter it in probability or statistics courses. And the basic premise behind it is that conditional probability is harder than you think. So I'm trying to promote a new problem to go in probability and statistics courses, which I'm calling Jackie's improbable sister, which is to show you that sampling is harder than you think. So this is not a new example. It's been written up in the American Statistician, Scientific American. Marilyn Vaux Savant wrote an article on it. I first encountered it in a John Allen Paulos book called Innumeracy, where it was entitled Mr. Smith's Children. So clearly the first thing to popularizing it is giving it a better name. And to set the stage, this story takes place in the town of Asymptopia. In the town of Asymptopia, every family has exactly 2 children. These children have equal probability of being male or female, and the genders of the 2 children in the same family are independent of each other. So if you know one of them's a brother, that doesn't necessarily give you information about the other one. And of course, because this is the statistician's version of Lake Wobegon, all of these children are exactly average. So Jackie is a girl in Asymptopia, and Jackie has a sibling. What is the probability that Jackie has a sister? So you ask a statistician this, and I say, obviously, probability is 1/2. You ask John Allen Paulos this in his book Innumeracy, and he says 1/3, without explanation. I found this so upsetting when I was reading the book, I actually had to put it down and go to the internet and look for errata, because I couldn't figure out how such a smart man could be so wrong. And when I thought upon the problem a little bit more, I realized Jackie either has a sister or a brother. The fact that we don't know which it is clearly doesn't make it a probability problem. But that's not the point I want to make today. No laughs, no frequentists in the audience. So what I actually found when I went to the internet is that this problem is famous for being ill-posed, which is to say, I can generate 2 sampling schemes by which to find my Jackies. And for one of these, the girls who are sampled will have a 50-50 chance of having a sister. For the other one, they have a 1/3, 2/3 chance of having a sister. And those 2 methods are equally consistent with the description of the problem. So how did this happen? It all comes down to how we found Jackie. So in statistician world, by the way, these are all the children of asymptopia. You pick a two-child family at random, you pick a child from that family at random, you can actually skip step one and just pick a kid at random. And if you picked a girl, well, 2 of those girls have brothers, 2 of those girls have sisters. This is how we get to a probability of 0.5. So what happened in Paulos' world? Well, basically, he thought that the key aspect of that description is that Jackie's family has at least 1 girl in it. So if I restrict all the families of asymptopia to those that have at least 1 girl, I'm down to 3. I pick a family at random. All of a sudden, I have a 2/3 chance of getting a family where the girl has a brother and a 1/3 chance of getting a family where the girl has a sister. So this is a contrived example, obviously, but it illustrates the point where you can draw incorrect conclusions if your sample didn't come from where you thought it came from. So for example, if I'm wandering around blithely thinking I'm in 1/2 land, and I'm given the statistics for 1/3 land, I will think something nefarious might be going on in asymptopia. When in truth, it was just that the sampling was performed in a different way than I thought. This is a very real and very expensive problem. So one of the places where it appears most often is public opinion polling. I could probably give an entire hour-long talk on this topic alone, but I'm just going to give you this one very famous example where the presidential election in 1948, the Chicago Tribune was having a dispute with its printers union, and it had to go to press before the polls had closed on the East Coast. If you were paying attention in 2000, you know it's not a really great idea to call a presidential election before the polls close. But they felt pretty good about it because all of the polls were in agreement that Harry Truman was going to get crushed. Dewey, the Republican, was going to win by a very significant margin. So they print this headline for their first edition. They publish it, and that led to the iconic photograph where somebody hands a copy of this newspaper to President-elect Harry Truman, and he says, "Ain't what I heard." Harry Truman was very pithy. So what happened here? Well, it turns out that the polling organizations were using the latest and greatest in opinion polling technology. It was something called quota sampling, which had allowed them to successfully predict several prior presidential elections. The way quota sampling works is that you slice and dice your population up according to different groups. So, for example, one group could be women between the ages of 25 and 35 who wear glasses and like math. And so you assign each of your pollsters a certain group, and you say, okay, go out and ask X number of people in this group who they're going to vote for president. They go out and they find these people, they ask them, then you perform some mathematical magic to recombine all of the different quota categories into one unified estimate of what the popular vote is going to look like. And this, as I said, appeared to work great up until 1948, but there was a magic word that I didn't say in my description of quota sampling. That magic word is random. So when people were picking their members of these classes, they got to pick whoever they wanted. For whatever reason, they kept picking Republicans. In fact, when they went back and they looked at the polling results in previous elections, they found that quota sampling had been oversampling Republicans for years. It just hadn't mattered up until this point. And so we abandoned quota sampling. Thankfully, we've solved public opinion polling. That's not a problem anymore, unless you're in the United Kingdom and following the parliamentary election, when, as you know, the Conservatives were going to lose badly enough. They might not be able to form a coalition government. Then we wake up the next morning, it turns out that the Conservatives had crushed everyone and they were going to be able to form a government all by themselves. So clearly, we still have a lot to learn about asking people who they're going to vote for. So here's an experimental example. This photograph is from the administration of the Salk polio vaccine. So for those of you who were born after the 1950s, you might not be terribly familiar with what polio was or why it was so scary. So polio was the impetus behind the formation of the March of Dimes. It was a terrifying childhood disease that was becoming increasingly prevalent in the United States in the early 20th century. This is the opposite of every other public health threat that we face, where we typically see less and less of diseases. Polio, we were seeing more and more. It primarily affected children. It caused incurable paralysis. In cases where it was affecting the torso, people could no longer breathe on their own, and they were stuck in machines called iron lungs that could breathe for them. And no one knew how it spread. People knew that polio was contagious, but they didn't know what the vector for spread was. In fact, if you want another example of extreme statistics, at one point, the prevalence of polio was linked to consumption of ice cream. And so people stopped eating ice cream because they thought it might cause polio. It doesn't, by the way. But the point is, when the Salk vaccine came out, it was heralded as the first weapon that we have against this terrifying disease. And the Salk polio vaccine trial is legendary in both biomedical testing and in statistics as being this fantastic, gold standard, randomized, double-blind control trial. And it almost didn't happen. So back in the 1950s, people said there's no way parents are going to agree to enroll their children in a randomized controlled trial. They're not going to let you inject their kid unless they know they're going to get the vaccine. We can't use this method. And there was great hue and cry and sturm and drang, and what ultimately happened was they split the trial into two parts. Half of it was non-randomized controlled. So they vaccinated second graders, and then they watched first and third graders as their control group. The other half, thankfully, they did do a randomized controlled trial. So I could give you another talk on what was wrong with the case control study half. But for now, let's focus on the randomized control sample. So I mentioned randomness is magic. There were actually three groups in this gold standard study. There were the people who enrolled in the trial, received the vaccine, people who enrolled in the trial and received the placebo injection, and there were people who did not enroll in the trial because their parents would not consent. It was about 200,000 in each of the enrolled groups and 300,000 in the unenrolled group. So remember I said we don't know how polio was transmitted, or we did not know at that time. Which of these groups do you think had the highest incidence of paralytic polio? Was the placebo group. Yep. And it turns out that this is not because saline injections are actually what causes polio. It was because of an uncontrolled third factor that was tied to both enrollment in the trial and susceptibility to paralytic polio, which no one suspected at the time. And that is that polio is a disease of affluence. So the vast majority of polio cases are actually completely asymptomatic. It's estimated that 90% of people who contract polio never show any symptoms at all. Of the remaining 10%, most of the time it's transient effects or flu-like effects, and it's only in 0.5% of people that you actually see this crippling damage and this horrible persistent disease. And the older you are when you get it, the more likely you are to have the severe side effects. So what was happening was higher income groups were living in more hygienic environments. They were not being exposed to polio as infants when they still had maternal immunity to protect them. So by the time they were eventually exposed to polio, they were more likely to catch the severe disease. This is why we were seeing more and more polio as time went on in this country. And it's also why the more highly educated, more affluent parents who were more likely to agree to the randomized controlled trial had children who were more susceptible. And so, as I said, this was a near miss. We actually did do the randomization here because if we had been directly comparing the group who was not vaccinated because their parents refused to the group whose parents consented and were vaccinated, we would have underestimated the efficacy of the vaccine. Randomization is pretty much the only thing we have to protect us from unknown unknowns. It's the only thing that is going to defend us against the aspects of our experiment we haven't even thought to worry about yet. And sometimes we can't use it at all. Here's a contemporary example. Google came up with a tool or an applet, whatever you want to call it, in I think 2008 or 2009 called Google Flu Trends. And this was heralded as this really neat method where what they were doing was they were taking people's Google search behavior and they were correlating it to the reported numbers of influenza cases that the CDC had in various regions of the country. And they found that people who are sick with flu are disproportionately likely to search for flu symptoms on the internet. And so it allowed them to correlate these search results they had access to the CDC data and predict where the flu season was going to go next and what its peak would be. And this was viewed as a really amazing achievement at the time. 2010 rolls around, Google Flu Trends breaks. It was actually under-predicting by a significant amount the flu epidemic in this country. So what had happened? Well, the flu changed. So 2010 was the H1N1 epidemic. It was the first sort of large-scale flu season that had appeared since Google started to field this tool. So Google's tool had never seen a highly epidemic flu strain, so clearly couldn't predict its behavior. They said, okay, well, now we've seen this, we won't make that mistake again. Google Flu Trends is fixed until 2013. So what happened in 2013? Well, Google Flu Trends starts over-predicting by a factor of 2 the amount of the number of flu cases that are being seen throughout the country. What happened there? Swine flu scare in Asia, which never actually translated to additional flu cases in the United States. So you have a lot of media attention, you have a lot of people Googling flu-like symptoms, who it turns out don't actually have the flu. So Google Flu Trends is once again fixed now. I tell you with perfect confidence, it's going to break again. The people at Google would not disagree with me because they are very clever and because they know they have a hard problem. They are chasing 2 moving targets. They are trying to correlate the behavior of the flu, which is always changing, to the behavior of humans on the internet, which is also always changing. So they are not worried about if their method breaks, they're worried about when it breaks and how they're going to fix it in time. This is a fairly low consequence example, but whenever you're dealing with basically changing behavior, which happens with a lot of human data, you have to be anticipating when your model starts working. And as I said, Google can't fix this. I'm sure that their X division is working very hard on their procedure for randomly sampling all times past and future. But until they get there, we will not be protected by the magic of randomization in cases like this. And so the point that I want to make with all of these examples is consider the source of your data, whether it's sampled or whether it's from a controlled experiment, in the same way you consider all the other factors that tie into your experiments. I mean, we know that if you're not very careful with experimental setup, you can get erroneous results. We have published plant genomes with human DNA in them. Obviously, lab contamination. If you set your clocks wrong, you think neutrinos can move faster than light. So this is just telling you to worry about the, I'm oversimplifying that one a lot. This is just telling you, think about where your data comes from. Think about how you're assigning your treatments in the same way that you think about all the other concerns you have when you conduct some kind of experimental study or observational study. So, in summary, please don't treat statistics like a black box. Don't treat it like a cookbook. Don't treat it like magic. If you receive a pitch from a software vendor saying that you don't need to understand statistics to be able to use these methods, don't believe them. Statistics is at once much simpler than this and at the same time much harder to execute because statistics isn't memorizing these enormous checklists. It's using your brain in fairly reasonable ways, and actually in ways that are very similar to the way you already have to think about problems in your own area of expertise. So, make sure when you are doing statistics, think about your problem. Make sure you always keep your end goal in mind because it can affect the data that you need and the methods that you can use. Make sure you understand your tools. It's not enough to know how they work. You have to know how they break because they will break. Assumptions are always violated. You just need to know when that's consequential. And finally, know your data. Make sure that the way you're collecting data or assembling data is going to reflect what you need about reality in order to solve your problem, and recognize that that is not as simple to do as it often appears at first glance. So I said at the beginning of this talk, I'm not trying to scare people off of doing statistics. I think most people can be successful at statistics when they approach it in this way. One of the reasons I think that is because you're already 2/3 of the way there. You already understand your problem better than anybody else. You already understand your data better than anybody else. If you were to call me and ask me for help, you would first have to explain those things to me, and that could take a very long time. The piece of this puzzle that might be missing, just because you did not spend 2 to 5 years of secondary education learning about statistical methods and then a subsequent 5 years reading the literature, you may not be aware of all the methods that are out there that could potentially help you. You may not be aware of all the pitfalls of the methods that you do know, and that's why we are here to help. So LLNL has a statistical consulting service. It will provide assistance for lab projects free of charge for up to half a day. And with that time, we're willing to do whatever you want us to do to help you with statistics. And that can involve going through papers and translating statistics into English. It can involve helping you write a proposal. It can involve helping you scope a study. It can involve giving you ideas for methods that you could try. It's whatever would be most useful to you. So on a personal note, the reason why I run this consulting center and the reason why I give this talk is because I am deeply concerned about the problems that I was speaking about at the beginning. I think it's tragic that we are having this crisis in reproducibility in science, and statistics is getting the blame, not entirely undeservedly. And one of the things I love about the laboratory is because I think if any place can fix everything wrong with statistics, it's here. And it's because we have a ton of smart people. It's because we're highly collaborative. We do naturally work together on these projects. And my goal is for every piece of statistical analysis that comes out of this laboratory to look like a trained statistician did it. I want to enable each and every one of you to be successful statisticians in your own area of expertise, and I am more than happy to help you in any way that I can. So on that note, I want to thank you all so much for being here today, and I look forward to working with you in the future.